Hi, welcome back to the Network Plus Certification video series. I'm Mike Redmond, Master Trainer, here to help guide you through your successful journey of becoming a Network Plus certified technician. We're going to walk through a wide variety of topics, starting with basic network concepts all the way through network management and security. In this segment, we're going to take a look at IPv6. We'll discuss the fundamental concepts of IPv6, describe some IPv6 practices, and show you how to implement IPv6 in a TCP/IP network. First, I'll start with the short introduction to IPv6. It all started with IPv4. Created in 1979, it is what we are most familiar with, the classic 32-bit IP address space, which provided for a little over 4 billion IP addresses. However, due to poor allocation methods, a lot of that address space was wasted, and we have since run out of IPv4 address space. Enter IPv6. It expands the 32-bit IP address space to 128 bits. It also improves overall security as well as routing. So it all starts with identification. How do you know that you're dealing with an IPv4 address or an IPv6? Well, you can tell from the colons. IPv6 address notation is 128 bits written in hexadecimal notation. A pair of colons represent a string of consecutive groups of zeros. And note that there's only one set of colon pairs per address. And just like IPv4, IPv6 offers an IPv6 loopback address. So instead of the 127 being home, now it's 1. Again, just like IPv4 in the APAPA address, usually noted with the 169, IPv6 has a local link address as well. The first 64 bits, or annotated as FE80, and then 2 colons, and then \64, is your local link address. Another important note is that just like the APAPA address, the local link address will only work on private networks. Now, the IPv6 subnet mask functions a lot like the IPv4. It's represented with CIDR notation, and no subnet is ever longer than a /64. This primarily is because the IANA only gives out /32 subnets to the big ISPs like Comcast. Those ISPs then pass out either /48 or /64 subnets. So most IPv4 subnets are going to be between /48 and /64. That brings us to multicasting. Multicasts have been around for quite some time. They existed in IPv4, and they will carry on in IPv6. And there are only specific applications that use multicasts. However, the functionality in IPv6 is just a bit different. Several IPv6 only multicast addresses were added. These are only going to be used for specific services like router messages. Ushering in the world of IPv6, we now see the end of the broadcast. Instead, each local link is going to be its own unicast address, and multicast addresses are now taking the place of the broadcast. Here we see the first major addition to IPv6. It is the anycast address. This address is going to be used for DNS. So technically speaking, the multicast is a broadcast in that every computer gets the frame, but only the computers specifically set up to process the frame can process it. Bear in mind, a computer must be configured as a member of a particular group to read a particular multicast. In this case, if a computer is a member of the all nodes, then it would read the message. Next, we have the addition of the global address. This is called the global unicast address. It's required for internet access. This address is what an IPv6 capable router will give to a host. The router provides the prefix, and then the NIC will generate the suffix using its /64 subnet. That brings us to the subject of aggregation. The current problem that we have is with the Tier 1 routers. There are no default routes. Basically, they have to process a monstrous routing table, 30 to 50,000 individual routes. With the advent of IPv6, it eases this issue because every router uses a subnet of the next higher router's route. This will overall reduce the size and complexity of those route tables, and it gives detailed geographic pictures of where each route is located. So how does it all work? Well, the gateway gives the first 64 bits of an IPv6 address to computers. The gateway gets its 48-bit prefix from an upstream router, then adds the network prefix. The ISP adds the next 16 bits of its subnet, and then at your own local gateway, the network technician adds the final subnet. That gives you your complete /64 subnet. So what happens if a route changes? Well, aggregation takes care of that. Starting at the Tier 1, a new 32-bit prefix is affixed to the address. Then downstream routers make an all nodes multicast to all clients to get a new IP address. IPv6 address changes are and will be somewhat rare. Next, let's take a look at how to use IPv6. Understand, for the purposes of illustration, I'm going to operate as if to assume that IPv4 is turned off. However, this is not actually the case as of today. However, it makes understanding IPv6 a whole lot easier. So the first thing that you should do is validate and verify that the operating system that you're working with is IPv6 capable. You can do this in Windows by typing in ipconfig, or in Linux or Mac by typing in ifconfig. Here's a list of operating systems known to be IPv6 compliant. The Network Plus examination expects you to be familiar with these operating systems. So the first important point to point out here is that NATing, or the network address translation, is not used in IPv6. That being the case, it means that all IP addresses are now going to be exposed to the internet. That's why IPv6 has IPsec built into it for those important security concerns. Additionally, you can handle additional security options by employing encryption and a firewall. Another function that works a little differently in IPv6 is DHCP. With IPv6, the address and subnet are received from the gateway router. And there are two modes to understand: stateful and stateless. Stateful works a lot like DHCP does in IPv4. However, stateless only passes out optional information. Stateless is the default and the norm. Another minor change with IPv6 is DNS. Note that most all DNS servers now support IPv6. However, there is a push to get DNS server information added to IPv6 router advertisements. If this happens, the need for DHCP version 6 might fall dramatically. So it's important to note that the details for DNS version 6 have not been finalized. For now, you have to manually add the DNS server information into your IPv6 clients. Next, we'll take a look to see if you're ready to move to IPv6. Understand, at this point, you can't be sure of the security of IPv6 in your environment, so you should not access the IPv6 internet from any mission-critical computer. For most of us, that description describes our personal PCs, considering that that's where we do a lot of our online banking and internet shopping. So when testing IPv6, you should only use a computer that doesn't contain your personal data and has not been used to connect to any other sites for banking or e-commerce. Now, that being said, there is what we call the gap between IPv4 and IPv6. So it's easiest to describe the gap by explaining what isn't ready for IPv6. Like most home routers and some internet routers are not ready to handle IPv6. However, when you look at what is ready, like most all operating systems, all root DNS servers, and all Tier 1 ISP providers, now you can begin to see where the gap happens. So to bridge the gap, we do what's called tunneling. We tunnel IPv4 to IPv6. This encapsulates the IPv6 traffic into an IPv4 tunnel. And then the endpoints receive the IPv6 traffic from an IPv6 capable router. So we refer to this as 6-to-4 tunnels. They are unique in that they don't require a tunnel broker and usually is only going to be configured between two routers. Also, they use a specific IPv4 address, which is 192.88.9.1, that is identified as the 6-to-4 unicast address. So it's easier to explain, however, it can be challenging to set up. So understand, when doing IPv6 tunneling, there's really only two options to choose from. 6 and 4, which is the most popular tunneling protocol. As a matter of fact, it's one of only two that is NAT traversal. The other being Teredo. It's built into Microsoft Windows, and many people have to use a third-party tool to configure it. Next, we have the Intrasite Automatic Tunneling Addressing Protocol, or ISATAP. It works within an IPv4 network. It basically adds an IPv4 address to an IPv6 prefix for the endpoints. So you heard me mention tunnel brokers. Well, a tunnel broker is someone that acts at the far endpoint. To configure the tunnel broker, you must know the tunneling standard and how to connect to that endpoint to create a true tunnel. Usually, this requires some custom-made endpoint clients. However, there are a few automatic configuration protocols available, such as the Tunnel Setup Protocol and the Tunnel Information and Control Protocol, the TSP and the TIC. So once connected to the IPv6 internet via a tunnel, you will have to deal with overlays. The overlay enables two IPv6 networks to connect via the IPv4 infrastructure. This runs as what's called a dual stack. It's when both the IPv4 and IPv6 protocols are running. And given the inherent insecure nature of both the internet and some of the unknowns of IPv6, it's recommended that you configure, at this point you'll have to do it manually, to run the IPsec protocol. So I guess the bottom line here is that IPv6 is here. The big switchover, if you will, it is coming. And at this point in your career, knowing IPv6 is paramount to your future. Well, there you have it. Pretty simple, right? I know, it can be a lot of information coming at you all at once, but don't worry, I'm here to guide you every step of the way. You can do this. Just remember, study hard, lots of practice questions, and you will succeed. You will become a Network Plus certified technician. I'll see you next time. Well, there you have it. Pretty simple, right? I know, it can be a lot of information coming at you all at once, but don't worry, I'm here to guide you every step of the way. You can do this. Just remember, study hard, lots of practice questions, and you will succeed. You will become a Network Plus certified technician. I'll see you next time.